everyone. In this video, we are going to look at parts of 11.2 and 11.4. We're going to specifically look at the convergence of power series, the properties of power series, and a little bit with how power series can help us with derivatives and integration of functions. So as I had stated before in the previous video, we're not doing everything in this chapter, so I'm just kind of touching upon those topics that will be on your test and that we're going to focus on. So the first thing I want to talk about is that idea of convergence. We saw it a little bit in the very first power series we worked on. Remember, we found that the summation as n goes from 0 to infinity of x to the n, which was a very basic geometric series. And because we understood the sum of a geometric series, and a in this case is 1, and our r is x, when x is between 1 and -1, we found when we did the graph that as we continue to add terms, our summation of x to the n started to wrap around the graph of 1 over 1 minus x. And it did that wrapping around only between -1 and 1. So, but that makes sense because we know in a geometric series, it only converges between -1 and 1. So again, when we looked at the graph, it's a quick reminder, I'll just review what that graph of 1 over 1 minus x kind of went like this. And then there was the piece down here, but we don't need to worry so much about that because we were centering our graph. Recall, this is centered at 0. You know, if we were doing x minus 3 to the n, it would be centered at 3, but we were centering it at 0. We said, well, between -1 and 1, as we started adding terms, such as 1 plus x squared, I think in our video last time on Desmos, we went all the way up to like x to the 9th or something, is our graph started to kind of between -1 and 1, and then it went off and did other things. But between here, it started to wrap itself around. So then I want you to recall from the last video that when we found the Taylor polynomial of sine x, if you recall. Taylor polynomial, that was a crazy word for polynomial, was equal to, if you recall, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on and so on. Now, in this case, as we added more terms to our sine function, right, what we found centered at 0, the more terms we added, the more it wrapped around. So maybe it wrapped around here, but as I added more terms, it continued to wrap around the function. So these are two different types of convergence. In this first one, we have what we call an interval of convergence. It will only ever converge between -1 and 1. But in the case of the sine x, we have what we call absolute convergence for all x. So let's write that up. All right, because there's also a third case. So for any, and we can go general, we don't need to just do Taylor series, for any power series centered anywhere, the convergence of a power series happens in one of the 3 following ways. So we saw examples for 2, but let's write them out. So we can converge absolutely for all x. Okay, that's what happens in the case of our Taylor polynomial for our sine curve. We are converging for all x, meaning as you continue to add those terms, it's going to continue to wrap around the function. When that happens, we say that the interval of convergence is negative infinity to infinity. And now I'm going to introduce a new term called the radius of convergence. Now, we are clearly working in two-dimensional space with an x and y axis, but if we talk about a radius, what I want you to realize as you continue in your math courses, especially if you go on to Calc 3, you're going to be working in three-dimensional space. So you're going to be working on the complex plane, in which case it is a true radius. So that's why I call it a radius here. Basically, the radius will make more sense when we look at part 2, in an interval. But right now, your radius of convergence equals infinity. Your radius is basically goes from the center to an end point. It's a distance from the center to the end. So in this second one, you'll get a better understanding of what we mean by radius. So now, again, number 1, it can converge everywhere, just like the Taylor polynomial for a sine curve. Number 2, I want you to go back and think of this example when we write out number 2. In number 2, if it converges on an interval, C to D, then we have a radius. And again, I want you to think of radius as a distance. It's going to be D minus C over 2. Now, I have to talk a little bit about this interval because I didn't write it out yet. If the endpoints, you must, when writing an interval, check endpoints. Because you have to see if by plugging in whatever value C is and whatever value D is for X and checking the convergence of that series, you need to determine what's happening on the endpoints. We know it's converging in the middle, so we know it's converging from C to D. What you don't know is if it's converging specifically at C and at D, in which case you have to do a test. So if it looks like this, it is converging at both C and D. Then you write it this way. You would write it like this if it's not converging at C and not converging at D, but converging everywhere in the middle. And then, of course, you can have it like this. Sorry, C. So it converges at C, not D. So you get the idea. And then CD, and here it converges at D, not C. And also your radius, if you think of a number line, right? And here I have C, and here I have D. Somewhere is the middle, right? This is your radius. It's a distance. So again, if I go back to this example up here, we know by definition of a geometric series, this is only going to converge when X, right, is between -1 and 1. But if you actually plug in, say, 1 in for X, you get the summation of n going 0 to infinity of 1 to the n, that is going to diverge. If you plug in -1, that's going to, since it's diverging at the endpoints, we say the interval of convergence is parenthesis -1 to 1 parenthesis. My radius of convergence, well, the middle point is 0, or you just do 1 minus -1 is 2. 2 divided by 2 is 1. The radius of convergence is 1. It's half the distance between them. Okay, so there's our two scenarios that we already have kind of seen examples of, but there is a third scenario that can happen when it comes to convergence. Sometimes a power series, and again, that includes all Taylor as well, converges only at the center. Remember, we call the center A. Only at A. If that occurs, then it has a radius equal to 0. So that means it's always going to converge at the center, because that's the whole way we set up our Taylor series and everything. As we add more and more terms, it's always going to go through that center point. But the problem is it doesn't converge anywhere else. So that is a third case scenario. So what we can do is some quick examples so you can see each of these scenarios. So let's look at some examples. For the first one, I want the summation k equaling 0 to infinity k factorial. So this is kind of like a geometric series x to the k with a k 1 over k factorial coefficient. All right, so what we want to do is find the interval. The directions are always going to read find interval and radius of convergence. All right. What you're going to find, you can use any of the series tests you learned in chapter 10, but what you're going to really find in this one is the ratio test is going to work real nice in most of these. You are going to be able to solve pretty much all of them a ratio test. And that's because we have that extra variable, that x in there. So the ratio test is going to work real nice. Plus it sets up a way to find that interval of convergence, because we know that it only converges when it's less than 1. So let's go ahead and do a ratio test on this problem. So to do a ratio test, you need your a sub k, which we know is x to the k over k factorial. And then you need a sub k plus 1. So how would we write that out? That is x to the k plus 1 over k plus 1 factorial. You also start to learn ways to write x to the k plus 1, right? You pull out an x, and then you have x to the k. That's a better way of writing x to the k plus 1, because eventually we want things to cancel. And then, of course, k plus 1 factorial can be written as pull out your k plus 1 and then have k factorial. That's going to help you a lot. If you recall, when you do a ratio test, you take your limit. In this case, it's k goes to infinity. What we're doing is a to the k plus 1 divided by a to the k. But a to the k plus 1, we just said, was x times xk over k plus 1 k factorial. Instead of dividing by a sub k, I'm going to multiply by the reciprocal. So much easier, because x is going to give me k factorial, because again, I'm going to take the reciprocal of that, over x to the k. What that lets me do is just cancel things out. So what cancels? My x to the k's cancel. My k factorial cancels. So here I am left with the limit as k goes to infinity of x over k plus 1. Now, There's a really important piece of the ratio test that I did not put in here, but let's go ahead and do that real quick. And we want to put absolute value signs. So again, if you recall, the original ratio test has these absolute value signs. They're going to play a really important part in coming up with these interval of convergence. So make sure you include the absolute value sign. I didn't do that first, but I caught on quick. Okay, so we have the limit as k goes to infinity of, now what you want to remember when you're doing limits, and you don't have to do this, but it's a good thought. You're only taking k to infinity, not x. X is kind of a constant in this case, so we can move that out front. It's not part of what we're taking to infinity. All right, we're just taking the 1 over k. So yeah, well, you know what the limit, if you put in infinity, you get 1 over infinity, which comes out to 0, of course. So this is going to end up being x times 0. So now I want you to think about which of the three cases this is. Are we setting up an interval, or it's either always convergent from negative infinity to infinity, or it's only convergent. So in this case, with okay, clearly that equals 0, right? Anything times 0 is going to be 0. With the ratio test, we have to determine when is it less than 1. Well, there's no x there anymore, so 0 is always less than 1. So if 0 is always less than 1, it is always convergent. So that means your interval of convergence is that negative infinity to infinity. Your radius equals infinity. So, and that's how you're going to write your final answer for that one with this work shown. Okay, so that example is that first one we looked at, which is converges absolutely for all x. Okay, and when that happens, is basically what happens is your limit goes to 0, your x disappears, 0 is always less than 1, so it's always convergent. All right, let's look at a second example. Number 2. So let's throw in an alternating on this one as well. It's always a little easier when there's not an alternating, but we'll put an alternating in this one. And then we have x minus 2 to the k over 4 to the k. So here we have a power series. And for this power series, well, we're going to check to see where it's convergent. And once again, ratio test. So you can take the time to set up your ratio test, or if you get used to it, you can just jump right into doing it. If you want to set up what your a sub k and a sub k plus 1 looks like, go ahead and do that. I'm going to jump right into the test here. So I'm going to take the limit as k goes to infinity. I'm not going to forget those absolute value signs this time. Now, again, I'm going to first start with my a sub k plus 1. So that's negative 1 to the k plus 1. All right, x minus 2. Now, let's here, we'll do this in blue for a minute. What does x minus 2 to the k plus 1 look like? Well, it looks like x minus 2 times x minus 2 to the k. If you write it this way, it's going to help you when you do your, when we cancel things away. So we're going to write x to the minus 2, x minus 2 to the k. Because technically it's k. When you use your power rule, k plus 1, that's what we have. All right, divide that by 4 to the k plus 1. Well, 4 to the k plus 1 is 4 times 4 to the k, because that together would make 4 to the k plus 1. Now all you're going to do is multiply by the reciprocal of your regular a sub n, which is going to be 4 to the k. We're just going to reciprocate our original series, negative 1 to the k, x minus 2 to the k. All of that's in an absolute value. Now let's talk about that alternating part for a minute, because here's the deal. We are under an absolute value. it doesn't matter. These negative signs, whether they're there or not, simply doesn't matter because they're always going to go away with the absolute value. So you can just get rid of them. That's what's nice about doing a ratio test with an alternating series. Now, I can get rid of my 4 to the k. Great. I can get rid of x minus 2 to the k, x minus 2 to the k. And let's write what we have left. We have left the limit as k goes to infinity of absolute value x minus 2 over 4. Okay, which now notice there are no k's left in this one. So the limit without an actual k is the only thing going to infinity. There's no k's left, so our answer is just whatever x minus 2 over 4 is. That's it. So pay attention to what happened. In that first example, my limit went to 0. There was no x left, and it was all real numbers, basically. In this one, my k is gone from my limit. So now I actually have this equation. What do we know about the ratio test? It's when the absolute value is less than 1. So we have to go back to some simple algebra here and determine, hey, what x values are going to make that absolute value be less than 1? Well, if you recall, back in algebra, that means x minus 2 over 4 is either less than 1 or greater than negative 1. That's how you work with an inequality and an absolute value with a less than. So we can work that inequality out. We get negative 4, x minus 2, 4. Add 4 to everything. And you add 4 to everything. We get negative 2 and 6. Now, this is where you do have to take a moment, because right now we have this interval from negative 2 to 6, but we don't know parentheses or brackets because we don't know what's happening at the end point. You have to check endpoints. So when you go ahead and check endpoints on this one, how do you check an endpoint? Well, first you check an endpoint when x equals negative 2, and then you check the other endpoint when x equals 6. What you're doing is plugging it back into the original with the x value. So what is that going to be when it's negative 2? That's going to give me the summation k equaling 0 to infinity of negative 1 to the k. Now I have x minus 2 to the k. Negative 2 minus 2 is negative 4 to the k over 4 to the k. Well, I want you to think through that one for a second, because the k values here and here are the same. So that's an important piece. When k is an odd number, they're both going to be odd. So the negative stays in both of them, which means you're going to end up with a positive, right? Like if you take negative 1 to the third and negative 4 to the third, you're going to have these two negative numbers, which are going to get multiplied together and always be positive. If k is an even number, they're going to always be positive. So those negatives almost go away, and this simply becomes 4 to the k over 4 to the k, which equals the summation 0 to infinity of 1, which means we're just going to keep adding 1 forever and ever and ever, and it's going to diverge on the end. It's going to diverge. Okay, a similar thing's going to happen over here. You have summation negative 1 to the k, but now I have negative 6, so I have negative 6. Oh, 6, not negative 6. Why did I have negative 6? It's 6. 6 minus 2 is 4 to the k over 4 to the k Well, the 4 to the k's are going to cancel. It's just -1 to the k. Yeah, it's -1, +1, plus -1, plus it still diverges. So you have -2, 6. That one was a little bit harder to determine the divergence and convergence. Some of the ones you'll do in the examples, it'll be a little bit easier to check those endpoints. So this is our interval of convergence. And then our radius. So there's a couple ways. If you put it on a number line, you have -2, -1, 0, 1, 2, 3, 4, 5, 6. It's going to be the center. The other way of doing it is 6 minus -2 divided by 2, which is 8 over 2 is 4, and you can see 4 is right in the middle. So your radius is 4. Okay, let's move on to the third one. Here we have the summation of 1 infinity k factorial x to the k. Do your ratio test. You can hit pause and try this one on your own, of course. So I have k plus 1 factorial is k plus 1 times k factorial. X to the k plus 1 is x times x to the k. We can just go ahead and put this underneath of it. This one isn't irrational to start with. All right, x to the k's cancel, k factorial cancels. What are we left with? The limit, as k goes to infinity, of k plus 1 times x, which equals the limit as k goes to infinity with the x out front. Now I have x times infinity. So let's go back to recalling what we're testing for in a ratio test. We need to know, when will that be less than 1? Well, because this is infinity, the only number you can multiply it by is 0. Which means this particular series will converge only at 0. And its radius of convergence is 0. So that's the kind of the other example. So for this video, I'm going to leave you with just the convergence. And then in the next video, we'll talk about some properties of our series and our integral of differentiation.